tremendous progress and a lot of successful citizen science programs. So for example, eBird is one of them, who collects the bird observational data from the general public and use that data to fit species distribution models to analyze the species distribution and migration patterns of bird species. And eBird has been tremendously successful. As you see the numbers here, we have 360,000 volunteers volunteered over 400 million observations into this data set. And the statisticians at the Cornell Lab of Ornithology, they use this gigantic data set coupled with remote sensing, land cover, weather, and remote sensing data. They're able to fit to date the most comprehensive and detailed species distribution models for hundreds of species across the Northern American continent, as well as all over the world. So you see that eBird is a very nice example characterizing the notion of citizen science. It actually combines the contribution of the general public into scientific discovery. Despite the great success of eBird, eBird actually suffers from a data bias problem, which is a common problem in citizen science. So here on the left, I'm showing you a heat map of where the observations are for eBird in continental US. As you see, this is a heat map, and the color of each pixel actually tells you how many visits there are in different locations. You see that these red locations, these are locations with a lot of observations, and in between of these red locations, the green locations means there are relatively few observations. And as you see that, despite the fact that there are a lot of observations all across America, if you zoom into one region, you see that the observations are centered around certain areas, and in between of these oversampled areas, you get these large green zones where essentially there are no observations at all. This is actually, it's not too difficult to understand where this data bias comes from. It actually comes from a mismatch between the participants' personal interests and the organizers' goal. So to engage people, citizen science programs such as eBird impose few or no restrictions about when and where and how the data should be collected. As a result, most of the data are collected in urban areas. This corresponds to those convenience locations that people often visit, or in those interesting locations such as state parks, national parks, and so on. This at a high level creates a very biased data collection profile, and it actually creates a challenge in terms of addressing the scientific goal of citizen science programs such as eBird. So if you really think about it, eBird is actually going to use a data profile like this to fit species distribution models for hundreds of species. And if you get this biased data collection profile, where in a lot of these regions, essentially it's a green region without many observations, you can't validate your model on those regions, letting alone fitting a very good species distribution model. So to address the data bias problem for eBird, we actually are proposing Avicaching as a two-stage game, following the principal and agent framework, in which we, as the eBird organizer, we use additional rewards to motivate eBird bird watchers to collect observations in undersampled locations. Now, the game roughly goes like this. Suppose there are no incentives, then bird watcher, they would visit their favorite locations, and these are the locations that they will often visit. And then we, as the eBird organizer, we offer additional incentives in the form of Avicaching points in this remote and undersampled areas to encourage exploration. And then the eBird bird agent, the bird watcher come again. The bird watcher would balance between his intrinsic utility of going into his favorite locations, as well as this additional rewards, and he will shift the sum of his effort to this remote and undersampled locations. So at a high level, this becomes a game between the organizer and the agents. So the organizer corresponds to the organizer at the Lab of Ornithology, And the agents are those eBird bird watchers who would like to go for their weekend trips to see the birds. And both the organizer and the agents have their utility functions, and they are subject to their own constraints. So here, this R is a vector of rewards that the organizer allocated to different locations. And then the V is a vector of, actually is the response from the eBird bird watchers. It's corresponding to which location that they choose to visit. And this V of org are the organizer's goal. This corresponds to that we are going to minimize the spatial bias. And the U of A are the agent's utilities. This not only take into account of the intrinsic utility, this corresponds to the interestingness and the convenience vector of the locations, as well as external rewards allocated by the organizer. Now, the difficulty in solving this problem is really, it is a bi-level optimization. So it has this agent optimization problem embedded in the global optimization. And this really makes this problem very difficult to solve. So we actually use novel embedding technique to solve this, this bi-level optimization problem. So we start with this bi-level optimization, and we have this agent problem embedded in the global optimization. What we propose is, first, we are going to approximate the agent decision process using a polynomial approximation scheme. This corresponds to that we assume the agent has bounded rationalities, which is a natural assumption to make. And this procedure encoding, it will take the reward vector as the input, and it will compute in polynomial amount of time what is the agent's decision R. And although it runs in polynomial amount of time, but this polynomial approximation scheme still doesn't fit quite well with this bi-level optimization problem, because to solve this bi-level optimization problem, you still have to go through every possible reward allocation, and there are an exponential many of them. And for each reward allocation, you compute what's the decisions the agents will take. And then you go through all these different reward allocations and see which one is the best. So it still doesn't fit quite well in terms of solving this bi-level optimization problem.
Yes, can you explain a bit more what bounded rationality means?
Oh, so bounded rationality means that we are going to assume that the agents are, they have bounded computational power. When they plan for their weekend trips, they don't calculate into the 10th digits after the decimal point. They instead they take some approximation algorithms. For example, they are going to say that I'm going to greedily select a few locations that roughly maximize my utility function, and so on. So this is I think it's a natural assumption that we make. And so we actually assume that the agent decision process can be captured by this procedure encoding, which is a polynomial approximation scheme. Now, what our contribution is that we are actually going to transform this procedure encoding into a declarative encoding. So for example, the Boolean circuit is a declarative encoding. And this at a high level is the knowledge compilation step. It's at a high level, it should always be able to, we should always be able to do this compilation. So for this time, you can actually, the agent's decision process can be captured by this polynomial algorithm. Then what you do is you compile each step of this polynomial algorithm into a Boolean gate in this Boolean circuit. And then you can do this knowledge compilation. So at a high level, this is always possible. But for the agent behavior model that we consider in our paper, we are able to do it a little bit better. So Boolean circuit actually doesn't scale quite well with our the constraint programming problem. So what we are able to do is we are actually able to compile the agent's decision process from a procedure encoding into a set of linear constraints. So these are constraints with binary variables. Now you might wonder, why do you would like to do this, transformation? Well, you start with this bilevel optimization problem, and you have this agent optimization embedded, and you don't know how to solve it. Now, if you can actually capture the agent decision process using a set of linear constraints, then what you can do is you can embed these linear constraints into the global bilevel optimization problem, and then the entire problem can be solved by a single optimization. So using this idea, this really allows us to scale to larger problems. This is because there are major developments in terms of constraint programming in the last few decades, and we are now able to solve problems with millions of variables and constraints. But they can only take, they can only work with this general optimization problem that you optimize an objective function subject to a set of constraints. They cannot take the bilevel optimization. They cannot work on the bilevel optimization problem. But if you can actually compile a bilevel optimization problem into a single optimization, that really allows us to take advantage of latest constraint programming solver and scale to larger instances. Now I'm going to give you an example that basically give you an example of how we actually embed the agent decision model into a declarative encoding, assuming that the agents are solving a knapsack problem using a dynamic programming approach. Now, I do want to emphasize that this is one of the agent behavior model that we consider in our paper. We do consider other more complicated agents behavior models. And for this particular agent behavior model, we assume that the agent has a set of locations to go. For each of these locations is associated with certain utilities to visit these locations. And then there are certain costs associated in terms of visiting each location. Now, what the agents are trying to do is solving this knapsack problem, which select a subset of locations within their travel budget so that they can maximize the total utility score. This is commonly known as the knapsack problem in computer science. We assume that the agents are using a dynamic programming approach to solve this problem by filling in a dynamic programming table. So here, the row of this table corresponding to different location sets, and the columns of this table corresponds to different budget levels. And ij's entry of this table corresponds to the best utility score the agent can get if the agent choose to visit the first I locations and under a budget level of j. Now the agency is going to filling in this dynamic programming table row by row. The first row is the boundary condition. There's no locations to go. So in this case, the best utility score the agent can get are 0. Then the agents start to consider the first location. It actually costs 2 to go to the first location. So if the budget is less than 2, then the agent cannot go to this location, so the utility is still 0. If the budget is more than 2, then the agent can afford to go to this first location, so the utility is 5. And then the agents are just filling in this table in some way. And let's consider the case that the agents are considered the first 2 locations under a budget level of 4. Now, the agents really have 2 options. The first option is not to visit the second location, by which case it's reduced to this case shown in the red box, and it has a utility score of 5. Otherwise, the agent visits the second location, which will give her a utility score of 7, but then she cannot visit the first location, so the best utility that she can get in this case is 7. So comparing these 2 options, and the better option would be this one that gives the agent a utility score of 7. Now, what I want to say is that we can actually use a set of linear constraints to mimic this dynamic programming approach. So for example, as we just talked about, this M24 entry is the best outcome out of these 2 different options. We can actually use 2 linear inequalities saying that this M24 should be at least the best of this M14 and M11 plus U2, okay? Now, of course, this gives only the lower bounds of M24. We do have to do some technicalities to take care of the upper bounds, but actually it's a trick, and it doesn't need to. I don't want to talk about this trick now, but the whole encoding is actually relatively simple, and it can be put in here. It's relatively short, but the core thing that I would like to emphasize is that we actually use a set of linear constraints to mimic the dynamic programming approach. Now, we apply our approach as a game called Avicaching in Tompkins and Cortland counties in New York State. And we identify a set of Avicaching locations, emphasize important landscape types. They are all public accessible, and all these locations receive 0 visits prior to the game. And we give people Avicaching points for their observations, meaning Avicaching locations. These mark their contribution to science. We maintain a leaderboard, as you see in the left, and they have their opportunities to win birding equipment, such as binoculars, from a lottery draw based on how many Avicaching points they have earned in a season. Now, the results has been phenomenal. We are able to shift 19% of birding effort from traditional hotspots to Avicaching locations. Remember that Avicaching locations, we select those locations to be the ones that are not visited prior to the game. So this 19% of shifting are a net amount of shift. And Cortland, as an undersampled county, receives 5 times more observations in 2015 compared to the previous 2 years combined. Now, we can look at the figures. So here, I'm basically showing you where the observations are in these 2 counties prior and after the Avicaching game. So in 2014, this is prior to the Avicaching game. The shaded area are these 2 counties. And I use the size of the doors to represent how many visits there are in different locations. As you see that in 2014, most observations are in Tompkins County, and they are highly concentrated. With the introduction of the Avicaching game, we are basically able to shift the observations to almost everywhere in these 2 counties. And this is show that there is quite a shifting happening in these 2 counties. So I introduced Avicaching, which received an amazing field response. And I would like to emphasize again that the core idea behind the Avicaching game is the idea of embedding, that we start with this bi-level optimization problem, and we have this agent optimization inside this global problem. And so it is a bi-level optimization problem. And what we propose is to approximate the agent decision process using a set of linear constraints. And then we embed this linear constraint into the bi-level optimization problem. And then it becomes a single optimization. Now,
so this approximation happens because you approximate the knapsack problem, not because
yes, it's because I approximate the knapsack problem. Okay, so I'm very fortunate to be the first speaker in the graduate student seminar, and I really would like to take this chance to thank Sebastian for allowing me to be the first speaker. And Sebastian actually asked me to talk a little bit about, how did my collaboration with the eBird team start. So here is basically the story. This is the history, and this is the gossip you want. So I started as a 2nd-year PhD student. At that time, I'm very eager to learn. But to be honest, I would, today, if I look back to the 2nd-year PhD student, I know that at that time I basically know nothing about research. And then, the eBird team, one director, one collaborator from the Cornell Lab of Ornithology, he approached Tara, who is my advisor, and me, saying that they would like a cell phone app to attract the bird watchers. They would like, this is smartphone age, and they would like to use the latest information technology to attract more birders into their eBird game. And this is really how it actually starts. So you see that there is actually a gap between what I want and what my collaborator wants. Right, so what I really want is a paper. It's a research paper in computer science. And what my collaborator wants is a cell phone app that they can use to promote eBird. And you will see that, you know, in a lot of these observations, a lot of these collaborations that I see today, that almost every student who wants to work on computational sustainability, they're going to experience this gap. Now, the problem is how we actually going to fill in this gap, right? The biggest lesson, and I would say the most pressure thing that I learned is that we would like to keep the conversation going. We would like to keep the conversation going to identify a scientific question, you know, by talking to those domain experts. So this is actually, so we went through multiple conversations.
Oh, sure. For you. Oh, you're
So the key lesson I learned is we have to keep the conversation going. So we would like to, you know, identify a scientific question by talking to domain experts. So we actually went through multiple conversations with my collaborators at Cornell Lab of Ornithology. And this is today, from the best of my memory, the outline of our conversation. So they approached us saying that they would like to have a cell phone app to recommend birding locations for bird watchers. And then I would like to ask, you know, what do they want that app to, which are the locations that they want the cell phone app to recommend, right? Do they want an app that recommends locations that they can see many birds, meaning in terms of quantity, many birds, or a cell phone app that recommends locations that they can see different kinds of birds? Then they told me that you know, they want a cell phone app that can actually recommend locations to see different kinds of birds. And then I asked him, you know, where do you think you will go to see different kinds of birds, right? This is basically, I asked him. So this is a question that basically asks domain experts with their intuitions, what are the best action to take? And then the experts talk to me that say that, you know, it's good, always good to try different habitats. If they want to see different kinds of species, they would, you know, visit different kind of habitats. It's a common sense that if you want to visit water species, then you want to go to the lakeside. If you want to visit a forest species, you want to go to the forest, and so on, right? So this is actually, we use this step to actually, you know, they actually told us their intuitions, and then that's really helped me to connect to a computer science problem. So I actually from there. So this is actually the last slide is ruled out because of this meeting software. But basically, I am able to discover that what they mean that they want to go to different kind of habitat is a coverage problem in computer science, right? So it looks like they would like to use as few trips as possible to cover a wide collection of different habitats. And so this is really connected to the coverage problem in computer science, and we can use some modular optimization to solve this problem. And so that is how we identify a topic, a research topic, out of this collaboration with my collaborators who initially would like to you know, do a cell phone app. But actually, we actually did a cell phone app in the end. So this leads to my first author paper in computational sustainability. And this is in collaboration with Vistra, Theo, Daniel Fink, and Carla Gomez and Steve Helling. And this has been published in the first AAA conference on human computation and crowdsourcing. And this conference actually happens in Palm Springs, in the desert in California.
No.
And so, one of the beautiful thing that you attend a conference in the desert is that you actually have the opportunity to meet your girlfriend. And it has been going quite well since then, except that we commuted pretty much from Ithaca to Cambridge. And the outcome is quite well. We are actually going to join Purdue University together as assistant professors this coming fall. So,
what conferences will be held in that place again?
So, okay, so later on, back to research. Later on, we said, we already did a paper that recommends locations to basically satisfy bird watchers' objectives. But we have scientific objectives for eBird. Can we also develop another app that recommend people to those locations in which the observations are mostly needed in terms of addressing the scientific goals of eBird? And then that was really how well the Avicaching game came from. And this again is thanks to domain experts' intuitions and their understanding of the eBird crowdsourcing game. So the biggest question we had was that now we are going to develop an app that's asking people to visit those locations that they don't really want to go, right? The first question is, well, they listen to you, right? If you develop an app nobody uses, then what's the benefit of that? But they have their great intuitions and their great understanding of this crowdsourcing program. So they said that they will visit those locations if you turn that entire thing into a game. And this is exactly what we did. So we actually used this gamification technology, and we developed Avicaching as a game, and that's really bringing in the later part all these nice results that you see in this talk. So I would like to end with a slide from Kala. And this is really saying that computational sustainability is a two-way street. So on one hand, sustainability-related fields, they offer new challenging applications and new methodologies to computer science. And on the other hand, computer science and related fields, they offer computational thinking and new methodologies that can really scale up the applications in sustainability fields and make their approaches applicable. So with that, I would like to say that I would have fun in this beautiful expedition for computational sustainability, and I would really take this chance to thank Sebastian for allowing me to be the first speaker in this series, and I'd like to thank everybody for your attention, and I'm ready to take questions.
So if anyone has questions in the audience online, you can write in the chat or just turn on your microphone if you have it. Yeah. Otherwise, I can ask you, do you see, is this project more or less in its final form? Do you see this idea being applied in different problems?
It's definitely not in the final form. We are actually going to scale this up, and the latest, so we run another year of Avicaching focusing on roadside bias. So most of the observations, if you don't have this gamification, most of the bird observations are happening alongside the road. Mm-hmm. And so we actually use this game to actually attract people to visit more off-road locations. So it has been even more successful, so the new results. And this year we are talking to eBird, and they are going to launch another game. It's also a Avicaching game, but it's in California. So there, the goal is more ambitious. It's basically, they would like to know the birds there, especially in the desert. So we are actually going to push people into the desert.
Oh, it's going to be tough.
And we will see if we can actually succeed.
Mm-hmm. Do you have any, did you want to say something?
Oh, in terms of pushing to other domains, I think we are also doing that. Yeah.
And maybe perhaps you could elaborate on how this idea of embedding was used in other contexts.
Oh yeah, the idea of embedding, we actually so the core in terms of Avicaching game is that it's a bi-level optimization that it's a game. So we as the organizer, we have to think about what those eBird bird watchers are thinking. And this becomes a bi-level optimization in CS, and we develop an embedding technique that can approximate this game, using a single optimization that allows us to take advantage of the off-the-shelf optimizers to solve this problem. And later on, we actually use the same kind of embedding idea. We are going to solve other problems in terms of making decisions in an uncertain environment, and that we have to take optimal policy controls that maximize the stochastic outcome. We also use similar ideas, and that is able to, we can generalize our method to a lot of different domains, from financial engineering to machine learning to robotics, to network design, and so on.
I have a question.
Mm-hmm.
Can you guys hear me?
Yes.
Okay. So I think I'm just not familiar with how Avicaching actually works, but you get a reward for seeing specific kinds of birds, or just for going to the location?
It's just for going to the location. So we actually thought about this question. Okay. So this is for going to the Pacific.
And submitting observation.
Yeah, and submitting an observation. So this is we actually consider this problem. It's in eBird, it's not only the positive identification of I see that bird that are. This identification is very valuable, but also negative observations are also valuable. So even if you go there and you see nothing, you can report that there are no birds there. That is also valuable in terms of addressing our scientific goal. And so in that case, we designed the game to be that if you go to that location and submit a checklist reporting anything you see there, it has to be a complete checklist, meaning that you reported all the bird species you see with your best effort, and then we give you Avicaching points.
I also had a question. If you could, can you hear me?
Yes. Yes.
Oh, okay. So thanks for the talk. It was really nice. I was wondering if you could talk a little bit about how you do the location selection process and how you might scale that up. So if you were to go to a new location, it sounds like right now you've sort of got two choices. Either somebody's manually selecting locations that are, accessible and unsampled, or you could use like all of the unsampled locations on some grid or some other definition.
Right.
But have you thought about, like, if you were going to try to deploy this in all eBirding locations,
right,
nationwide, how might you scale it up?
Nationwide. So in this game, indeed, the locations we are selecting, yes. The biggest concern we had in these two counties was they have a lot of private land that we cannot trespass into those private lands. In terms of larger scale, I think we can actually use the species distribution model to inform us what are the best locations to select. What is the best set of locations that when you actually get the data from those locations, that will help you improve the species distribution model the most. I think that is a way to scale this to larger scale.
Uh,
I assume I missed this at the beginning. I'm sorry for being late.
no,
So if you could select among previously reported eBird locations
Yes.
and then assume that they're publicly accessible.
Right. Yeah. I think this is a good idea. Yeah.
but part of the motivation is to get people to go to new locations too.
Of course.
Yeah, that's the challenge.
Okay, then do we have more questions? Otherwise, we can conclude this first seminar. Yeah? Okay, so thank you again, Yexiang.